Hello and welcome to a new video for Pre-Algebra. This is lesson 10 in Math UC. We're going to be talking about the Pythagorean Theorem. If you would like to go to my website, you can download a free notes page to go along with this video so that you can take notes and look at them later as you're working through problems. Let's start with some vocabulary. So if you're using that notes page from my website, then you'll need to fill in the blanks here for these vocabulary words. So we're going to be talking about a theorem today. A theorem is a statement that can be proven true. In math, we like theorems. We like to know that what we're talking about is true. So there's so many theorems, there's lots of them, and this is going to be one that we look at today, so get excited. This theorem has to do with right angles, right triangles, and the parts of a right triangle. So hopefully these are some things that you've seen before, otherwise they might seem a little weird, but a right angle is an angle that has a measure of 90 degrees. 90 degrees is the angle of that a wall and a floor are supposed to make. I don't know necessarily how to explain what 90 degrees is other than, our corners of our paper are 90 degrees, things that line up like that are 90 degrees. So we signify a 90-degree angle in a special way. If you see the triangle that's on the screen right now, if you see that there is a box at the bottom left of it, that is showing us that that angle is a 90-degree angle, or in other words, it's a right angle. Because this triangle has a right angle, it is called a right triangle. So there are special things we can do with right triangles that we can't do with other kinds of triangles. And this theorem is one of them. In order for us to use the Pythagorean theorem, we have to have a right triangle. Some other parts to a right triangle is we have the hypotenuse, which is the longest side of our right triangle, and it is always across from the right angle. There's actually a connection between angles and sides on a triangle, that the biggest side is always across from the biggest angle. The smallest side is always across from the smallest angle. So the right angle, because it's 90 degrees and our triangle has to add up to 180 degrees, that 90-degree angle has to be the biggest angle, so the hypotenuse, which is across from it, has to be the biggest side. You can kind of help yourself figure out where the hypotenuse is if you pretend like this box is actually showing you an arrow and it's pointing at the hypotenuse for you. So this side would be our hypotenuse. Then our other two sides, we don't have a special name for them individually. They are both called legs. So we might call one of them shorter or longer, but they are the legs of our triangle. So basically you have a hypotenuse and you have two legs. And that's the vocab that we need for the most part. We're also, though, in this lesson going to be using things that we've done over the past few lessons. So we're going to be squaring things, we're going to be square rooting things, and we're also going to be solving equations, which is something we did in lesson 9. So it's really cool when we get to combine things that we've learned. And it's also cool that this is something that maybe you can see an application to in the real world. If you look around, you may not see right triangles all around you, but you probably see things that meet at right angles, like the floor and the wall and the ceiling. Most of our furniture meets at right angles, right? That tends to be more than half of the things that you see around you probably have some sort of right angle somewhere in them. And so then it becomes a thing of, well, how does the Pythagorean theorem help? How could I make a triangle out of this and then have the Pythagorean theorem be helpful in some way? Let's check it out. So the actual theorem, the Pythagorean theorem, it says, and there's different ways to word it, so this is one of the ways that it said. It says, in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. More commonly, what we see and think of it as is this formula, basically. A squared plus b squared equals c squared. And the only thing that we need to really define here about that formula is that a, b, and c are the sides of our triangle. They will normally, at least two of them will normally have to be numbers, and we can then use those two to find the third thing that we're missing. And then C has to be the hypotenuse, but A and B can be either of the two legs. Because what we're saying here is that since the hypotenuse is the biggest, we can actually take the side A and B, square them, add them together, and that should equal what the third side is squared. So this is kind of a really cool thing. It's not kind of a really cool thing. It is a really cool thing. It's really cool for a lot of reasons. I don't want to take a ton of time in this video to go off on a tangent about like history of math, Pythagorean theorem. Maybe someday I'll have a separate video on it, but I'm going to link a couple videos in the description that have some cool information that I used while I was preparing this to just kind of wrap my head around some of the history around it, and also some of the ways that we can prove it. Because since this is a theorem, that means that it can be proven to be true. And this actually has a whole bunch of different proofs to it because it's been around for a really long time. So if you were to search proof of Pythagorean theorem, you're going to find a ton of results. But this is the theorem itself. We're going to use this to help us with finding the sides of a right triangle that we don't know. All right, example 1 says use the Pythagorean theorem to find the length of the unknown side. Now, a quick note, these apostrophes that I have on here are a way that we represent feet without having to write out feet, or even without having to write out ft. So this is saying that we have a right triangle. We know it's a right triangle because of the box that's in one corner. That this right triangle has a leg that is 3 feet long and another leg that is 4 feet long. And what we don't know right now is how long is the hypotenuse. But because this is a right triangle, it has to be true that a squared plus b squared equals c squared. So what are a, b, and c in this situation? Two of those have a little bit of have two options. Two of those have two options of what they can be. A and B have to be 3 and 4. It doesn't technically matter which one you put in which spot. You just have to realize that one of these is supposed to be A and one is supposed to be B. What's important is that H is C. In this case, we don't know what H is, or we don't know what C is, but that's what that side is supposed to be. So let's plug this in. We're going to do 3 squared plus 4 squared equals, we don't know C. We could either put C squared here or H squared here. It doesn't matter which of those two letters you want to put in. But since we're trying to figure out technically what H is, that's why I've put H there instead of C. Let's work this out. Quick reminder on order of operations, or maybe this is new information on order of operations. It matters what order you do the squared and the sum here. We need to square the 3 and square the 4 and then add them together. If we add 3 and 4 together first, that would have to have parentheses around it for us to know that that's what we were supposed to do. This is not saying add 3 and 4 and square, which is what I've just written. It's not saying to do that. It's saying, hey, what is 3 squared, which is 9? What is 4 squared, which is 16? Let's add those together and get 9 plus 16 is 25. And that's what h squared equals. So what we've just found is what h squared is. What would that mean h is? Because that's what we actually want, is to know how long h is. So what do we use to figure that out? If h squared is 25, how can we figure out what just regular h is? We will need to square root to figure this out. The square root of 25 gives us 5 because it asks us what times what is 25. And the square root of h squared is just h. So what we found here is that h, our missing side, is 5. Let's go back and look for units though. This is in feet, so it's 5 feet. And then we can circle it and say, hey, we're done. That's how we use the Pythagorean theorem to find the unknown side, in particular to find the unknown side when the unknown side is the hypotenuse. Example 2, Pythagorean theorem again, but this time, instead of our hypotenuse being missing, one of the legs is missing. So we need to do something a little bit different. It's going to start off in a similar way though, of just saying, okay, this is a right triangle, so this is a squared plus b squared equals c squared. let's identify, okay, which of these sides is the hypotenuse, because that's what matters most, is making sure we've got that one right. So the 13 and 2 quotation marks, or 1 quotation mark, which is 2 apostrophes, this is telling us this is in inches, by the way. So 13 inches is C, because that's our hypotenuse. It's across from our right angle. Then 5 inches and L are our other 2 legs. Again, it doesn't matter which of these two you label A and which you label B. I probably have a habit of labeling, if there's one farther left, A, or if there's one like higher A, I don't know, because you can kind of twist the triangle around and have it look different. It doesn't matter which one's A and which one is B. We should still end up with the same answer. So let's do 5 squared plus B squared, which is labeled as L, so L squared, and then C squared, which is 13 squared. Now I think it was about a couple weeks ago, or a couple lessons ago, that we did exponents. I'm thinking of when we did square roots. So when we did square roots, I went through and had us do square roots up to 144, which is 12. The square root of 144 is 12. So if you have notes on that, then that might help you as you're going through this, because it might help you say, okay, well, I know everything up to 12 squared, basically. But this is 13 squared, so what do we do whenever we don't know what it is off the top of our head? We come over here to the side, and we work it out. I actually happen to know what 13 squared is, though. It's 169. At one point in my life, I had all the way up to 25 squared memorized. I don't have all of them memorized anymore, but I do have 13 squared still. So 5 squared is 25, L squared is still L squared, 13 squared is 169. Let's think back to how to solve equations and think, well, how can I make this so that instead of 25 plus L squared, I just have L squared? I will subtract 25 over to both sides. And that means that L squared equals, let's see, that would be 144, which I just mentioned a second ago, right? The square root of 144 is going to be 12, so that means L equals 12. I forgot my units. This is actually 12 inches. Better put that back. The other thing that goes along with this then is that in order for us to know we have a right triangle, our sides should work for the Pythagorean theorem. It's actually called the converse of the Pythagorean theorem, which is a fancy word for like saying, let's switch this around. So if we go back and we look at what the theorem says, it says, in a right triangle, this is true. So the converse is to say, if we have this situation that the square of the hypotenuse is equal to the sum of the squares of the other two sides, then I know I have a right triangle. That's what the opposite of it says. So what we can do is we can actually say, if I have 3 numbers and I think they form a right triangle, I can plug it into the Pythagorean theorem and find out for sure if I have a right triangle. So that's what we're going to do here on example 3. We've got 4 situations that we're going to check to see if what we're given represents a right triangle or not. So the only thing, again, that we have to worry about as far as labeling A, B, and C is that C is the biggest side. So since these are actually from least to greatest, it makes a lot of sense for us to just say, okay, 2 is A, 3 is B, C is 5. But what was most important there is that C does have to be 5. So what we're going to do is we're going to say, okay, 2 squared plus 3 squared equals 5 squared. Is that true? If it's true, we have a right triangle. If it's false, then we don't have a right triangle. We don't really know anything else about the triangle. We just know that it's not a right triangle. So 2 squared is 4, 3 squared is 9, 5 squared is 25. Is it true that 13 equals 25? No. No, it is not. So we'd say that this is not a right triangle for our answer. Okay, at some point along the way here, you probably are like, okay, I can do this on my own. It's great to try that ahead of me. So you can pause the video to try these and then start it back up once you've got an answer to see if you were on the right track or not, or start it back up if you get stuck. But it is a good practice to kind of try these things once you think you have the hang of them. So this is going to be 6 squared plus 8 squared equals 10 squared. And we're asking ourselves, is this true? So let's see, 6 squared is 36, 8 squared is 64, 10 squared is 100. Is it true? Is 36 plus 64 100? Well, yeah, it is. 100 equals 100. So we'd say yes, it is a right triangle. Okay, let's look at 8, 10, and 13. So A, B, C, 8 squared plus 10 squared equals 13 squared. Is that true? 64 plus 100. And remember from earlier, 13 squared is 169. Well, 64 plus 100 is 164. That's pretty close to 169, but close is not good enough. Those do not equal. So C is not a right triangle. And D, 7, 24, and 25. So A, B, C. So we do 7 squared plus 24 squared equals 25 squared. Well, we've got some big numbers here. 24 squared, I don't know off the top of my head, even though I did it yesterday. Let's see. $576. And 25 squared, I do know, is 625. So is it true that 49 plus 576 equals 625? We might need to come over to the side to do that so that we can like line up our place value and carry and all that. And you know what? It is 625. So this is yes. It is a right triangle. So we had 2 that were right triangles and 2 that weren't. And if you start thinking about it, we've got lots of numbers, lots of whole numbers, right? And there are actually very few that will give us a right triangle. So that actually ends up meaning that we have a special word for whole numbers that do work to give us a right triangle. They're called Pythagorean triples. So Pythagorean because of its relation to the Pythagorean theorem, triple because we've got 3 numbers. Here is a short list of some of our Pythagorean triples. You can Google Pythagorean triples and find a longer list than this, but because we tend to aim towards smaller numbers, just because they're easier to work with, these are some of the ones that we have. So 3, 4, and 5 we saw on the first example. 6, 8, and 10 was in example 3. 7, 24, and 25 was in example 3. 5, 12, and 13 was in example 2. So you may see as you're working through this, because we're going to keep trying to solve these with where we don't have to worry about getting decimals or anything for our square roots, we should see a lot of these kind of repetitively. So if you wanted to, you could memorize these. The only one I really have memorized personally is 3, 4, 5, because they're right in a row. And I'd say the next easiest one to probably memorize is 5, 12, 13, because I guess it's not the next one. 6, 8, and 10 is a Pythagorean triple because it's double 3, 4, and 5. So actually we could make a lot more Pythagorean triples just by taking 3, 4, and 5 and multiplying all of those digits by the same number, because it is proportional or is a multiple of that. It would also work. But that's the idea. But that's the idea of what a Pythagorean triple is, and gives us an idea of just how rare actually it is that we have 3 sides that are all whole numbers. What that ends up meaning, though, as far as real world application is, in the past at least, one of the things that they would do to make sure that they were getting right angles, ancient Egyptians, we have evidence that they did this, they took a rope that had 12 knots on it to show a length of 12, or they had it like segmented so they could see that it was a length of 12. And then they would say, okay, let me take three lengths, and then let me turn the rope so that I've got 4 lengths, and let me turn the rope again so it meets back up. And that gave them a 3, 4, 5 triangle, which they knew gave them a right angle, which is what they wanted. So they could use this to help them make sure they were getting right angles or things like that. Like I said, there's a lot of history and a lot of cool videos out there about this, and I'll link a couple in the description in case you're interested in finding out some more about the history of the Pythagorean theorem. As always, thanks for watching. If you are not subscribed, please subscribe, like the video, leave me a comment if you'd like to, and as always, you can check out my website, KStevMath.com, for more resources, and I look forward to seeing you in the next video. Bye.